In this lecture we're going to discuss the equilibrium of beams. This will be a review from statics, but what I've often noticed is that it takes being in mechanics materials sometimes to get a really good understanding of statics. And beam statics for us in particular is going to be very important because we're going to be very interested in stresses in beams in a couple of lectures. We'll derive the formulas for shearing stresses and bending stresses in beams. And beam loading is a very, very common way that different structures are loaded. So let's first just define what a beam is. A beam is a long structural member that can support transverse loads. So here I have sketched a simply supported beam. There's a pin over here on the left and a roller over here on the right. And what I mean by transverse loads is if we look at this beam, the axis of the beam goes down that way, so that's the plus x direction. And transverse or perpendicular to that could be some forces, maybe some bending moments, some sort of distributed loads on the beam, and these loads are acting perpendicularly to the axis of the beam. The fact that it's a long structural member, what that means is that its cross-section dimensions are small in comparison to the length of the beam. And the exact number maybe depends on what you're looking at, but somewhere between 5 to 10 diameters or major cross-sectional dimensions of our beam would make up the length to be considered a true beam by the ones that we're looking at in our class. So we can look at different kind of beams. Let's look at a review of statics of beams, support reactions, and so forth. So let's look at free body diagrams and reactions. One way we can support a beam is with a wall or a cantilevered support. So maybe this wall over here is position A, and I put a force over here at position B, and the force of that is the force P, and the length of the beam is L. If I draw the free body diagram of this beam, remember a good free body diagram is one where the supports are removed and replaced with the appropriate reactions. Then the wall can support two perpendicular reactions, and it's usually convenient for us to put those in a horizontal and vertical direction, although we do not need to. It's usually easy to do that. And the wall can support a bending moment. So I'll call that MA. Here's my length of the beam, L. And if I notice, I have three useful equations of plane statics, plane or planar statics. I have the summation of forces in the x direction, which in this case would say AX equal to 0, so I don't have any axial forces applied to this beam. We have the summation of forces in the y direction. We have AY minus P equal to 0. That gives us an equation where we can solve for the reaction in terms of the applied load. And we can do the summation of moments about any point that we want. If we do point A, then we would have MA minus P times L equal to 0. So those three planar statics equations can be used to solve for our beam reactions. For a simply supported beam, if we wanted to draw the free body diagram, simple supports are usually pins and rollers. Try to draw that straight. There's my pin connection, that's how I represent the pin, and here's the roller connection that I have here. And maybe we have a force and a moment that we can put on that. We can put other loads on that as well, as we saw. But the reactions at the supports then would be for my pin support, I can have two perpendicular reactions. If that's point A on the left, maybe point B on the right. And my roller reaction can support a reaction that is perpendicular to the surface on which the roller is resting. Usually that means in the vertical direction, so we'll just label that as BY. Now there's one thing I want to point out about these roller connections in particular. Schematically, they're represented like a ball or a marble that's just sitting on a table. We have maybe a ruler that sits on top of that. While that is a fine representation of a roller type connection, the idea is that it allows for translation in the horizontal direction while restricting any translation in the vertical direction. So in real beams that could support loads that go both down and up on a beam, the roller is really a captured roller type configuration. It doesn't lift off the surface if we put an upward force on it. So again, I just want to emphasize that what I draw on these pictures are schematic representation of actual pin and roller type supports. They can be simple, they can be kind of complicated, but schematically, and to reduce it down to basic statics, we can represent the pin connection with two forces. I need an X over here, and the roller connection with one force. And we still have our equations of planar statics. Again, the summation of forces in the x direction, summation of forces in the y direction, and the summation of moments about a point equal to 0. Now if you notice on these equations that I just wrote down, I put in my direction and I put an arrow and I put in a direction in which my summation of forces or moments equation is positive. So if you just write this equation down, it's not very helpful. To make it as helpful as possible, if you complete this symbol by putting a direction of positive, then that will help you get all the terms correct. You probably do all right with summation of forces and summation of in the x and in the y, but in particular summation of moments about a point, it's very helpful if you indicate which direction of rotation you're considering positive. Since these equations are set equal to 0, it doesn't matter which way you call positive or negative. The equilibrium equations will be equivalent. So for these external reaction equations, the direction in which you draw these supports and do your equilibrium equations doesn't matter. If I end up with a negative sign for a value of a reaction, all that means is that the reaction points in the opposite direction from what I have assumed. So for example, let's do a different color. In my cantilevered beam, you'll notice that I have my reaction AY equal to P. This is a positive number, and what that means is that this reaction AY really points in the upward direction. Let me draw another free body diagram. Okay, so I've drawn a free body diagram of my same cantilevered beam, and I'll do the summation of forces in the y direction again. I'll say upward is positive, and in this instance you'll notice that I have AY pointing downward, so my equilibrium equation will say minus AY minus P is equal to 0, or if I solve for AY will be equal to minus P. Well, what does that mean then? It means that this force P, this force AY really points upward and has the value of P. And in both cases, the free body diagram on the very top and the one on the very bottom are equivalent because they both have a force P that points upward. So let's just make a note of that. A negative sign on a reaction just means that that reaction points in the opposite direction from what you have assumed. Now, in order to know which direction you have assumed, you have to draw the free body diagram. Free body diagrams on all these kind of problems in statics and in mechanics materials are very essential. If I just say AY is equal to P, there's no context for it unless you also include what the free body diagram directions are indicating. Right? So I will look for good and proper free body diagrams. Now there's a few more things that we need to review about beam statics, so let's get a fresh page here and we'll write those down. Right. If you have a distributed load on a beam, for purposes of finding reactions, distributed loads can be replaced by concentrated forces applied at the centroid of the distribution. So here's a couple of examples. Suppose we have our cantilevered beam of length L, and we have a triangular distributed load on it. And the height of the distribution over at the wall is, let's say, W0. Well, I can do my free body diagram and I can find my reactions at the wall. I can list them down. I know because it's a cantilevered beam, I can have a moment at the wall, I can have a force in the horizontal direction, I have a force in the vertical direction. Let's say if this is point A, we'd have AX, AY, and MA. And then I have my load that's on this beam. Well, if I have a beam that's a cantilevered beam, just like I have here, same length and everything, and if I replace this distributed load that's a triangular distribution with a statically equivalent force, what that means is it has a force that's equal to the area of the distribution. So in this case it would be 1/2 the base times the height of that load distribution, pointing downward like the distributed load is. Then the reactions of that beam with that concentrated force would be the same as the reactions of the beam with the triangular distributed load. Okay, so those two beams have the same reactions. Now I do want to emphasize that the reactions are the same, but there are other things in the beam that might be different. Later on we're going to talk about deflections of beams, or how much the beam bends downward due to that force. The deflection of a beam with a single point load on it is going to be different than the deflection of a beam that has a triangular distributed load or some other load distribution on it. So not everything is the same, but for purposes of finding the reactions, the statics of those two beams will be the same. Well, the next thing we want to talk about are internal shearing forces and bending moments, which is something that you would have seen in statics when you drew your shear force and bending moment diagrams. And we'll do the same thing in our class. We will draw and sketch shear force and bending moment diagrams as well. Now the internal shearing force and bending moment inside of a beam are directly related to the stresses in beams. They're going to cause shearing stresses and axial normal stresses in our beams. And there's a very definite sign convention that we're going to use. It's the same one that you would have used in statics for shear force and for bending moment. If we have a beam and we cut a section of our beam out, so this is along the axis of the beam. If we have a force that goes down on the right side and up on the left side, we're going to call that a positive shear force. Now this is not a free body diagram that I've drawn. This is just a section of a beam with our shear force on it. So if it goes down on the right and up on the left, that's a positive shear force. And if it does the opposite, then we'll consider that a negative internal shear force. Okay, so up on the right and down on the left is negative internal shear force. Now the interesting thing that I always think about is, well, left and right kind of depends on which side of the beam you're looking on, right? Correct? So if we're on one side of the beam, things may look a different way. If we're on the other side of the beam, things may look another way. Well, this sign convention is looking at our beam in a right-handed coordinate system where the x-axis goes to our right and the y-axis goes upward. So that's just to keep our orientation straight. And we'll see the consequences of having that. Now, this is an arbitrary sign convention. We don't have to use this sign convention, but everyone does. And every mechanics materials book and every statics book will use this sign convention. There's also a sign convention for the internal bending moment. The internal bending moment for a section of a beam, let's draw it straight, here's my cut, is such that it puts the top of the beam in compression. And likewise, if we cut away part of our beam and the bending moment goes this way, then that means the top of the beam is in tension. We have a negative bending moment. Now if you take a ruler or a pen that you might have and you bend it up and you bend it down, part of the beam is in tension and part of the beam is in compression. A positive bending moment puts the top of the beam in compression. Now if I were to sketch this as it might look like when it's deformed, then it would kind of curve this way for a positive bending moment. Some people say that's like a smiley face. And it would curve the other way for a negative bending moment. Kind of exaggerate this a little bit. Sometimes the way I like to think of it is if you see this moment, it kind of looks like it pulls out from the bottom and it pushes into the top. The bottom is in tension and the top is in compression on the left and right sides. And likewise in these arrows, they're pulling out from the top and pushing into the bottom, indicating tensile stresses on the top and compressive stresses on the bottom. These are our sign conventions for shear force and bending moment. We need to just memorize them and go with them, but we'll have plenty of chance to practice the sign convention for internal shearing force and bending moment. If we stick with this sign convention, that's going to make life easier when we go to determining the sign of our stresses in our beam materials. And that can be really important. A lot of materials like concrete, a lot of brittle type materials, construction materials in which beams are made out of, have different properties in tension and compression. They might be very weak in tension and very strong in compression. So it can make a whole lot of difference in your beam design if you don't keep track of the sign of the bending moment and the sign of the stresses in those kind of beams. So let's do a couple of examples. We'll start with one that's relatively simple and we'll kind of build our way up. Some more complicated examples. But for this example, I have a simply supported beam. I have a pin and a roller, again shown with the schematic representations. And this beam is a length L and has a constant distributed load, a uniform distributed load of W0 applied to it. We want to find the internal shearing force and bending moment at the midspan of the beam. Now what the midspan of the beam means at L/2. Well, the first thing we want to do is we want to find our beam reactions. Now if I look at this beam, I could write down what the reactions are because I know that each support reaction takes half of the applied load. But let's go ahead and do it more formally so that we don't skip through any steps. We're going to draw a free body diagram. We know that we have the pin reaction here. I'll call that point A. So maybe we have an AY and then an AX. Now there aren't any forces in the X direction, so we know AX is going to be 0. But I think it's always a good habit to go ahead and include this reaction anyway, because we'll be working problems later on where we will have reactions in the X direction. Okay, now I have my applied load of W0 that goes along the length of the beam. And the length of the beam is L. So for my statics, I have the summation of forces in the X direction. If you notice how I'm putting the sign convention in here again, I have AX, and there's nothing else, so AX is equal to 0. Summation of forces in the Y direction, okay. I have AY, and we mentioned previously that we can replace the distributed load with a statically equivalent concentrated force or that force is equal to the area of the distribution. In this case, we have an area of a rectangle that we need to deal with, and that area is W0 times L. So the statically equivalent load is pointed downward, so value W0 times L, and then I have plus By equal to 0 for equilibrium. Now my unknowns are the reactions AX, AY, and BY, and my knowns are the length of the beam and the value of this distributed load. Even though it's in terms of symbols, it's something that we could put in 100 pounds per foot, 20 newtons per meter, something like that. Then our other equation that we're going to use is the summation of moments, and we can do any one particular point that we want to get a unique equation. Let's do the summation of moments about point A. And again, I'm putting my sign convention in here. So if we start on the right-hand side, in my positive direction of rotation, I'll have By times the length of the beam L. I'll have minus W0 times L. That's the statically equivalent concentrated force. And then I have L over 2, which is the moment arm from position A, because this is the location, the centroid of the rectangle is located at L over 2 from position A. And let's see, I don't have anything else because the moment arm for AX and AY are equal to 0, so I can just write equal to 0 for equilibrium. Now from this third equation, the L's cancel out, and I can see that By is equal to W0 times L over 2, and if I put that back in here and solve for AY, I will also find out that AY is equal to W0 L over 2. So let's draw the free body diagram of this beam with my reactions put in their correct directions. Both of these reactions turned out to be positive, so they really do point in the directions that I assume them to point. Now another thing I want to point out is that notice that I am not putting the equivalent load back on here. I am putting the actual load distribution that's on this beam. Okay, so step 1 is to find the reactions, and then step 2 is to make a free body cut at the point of interest. And put my internal shearing force and bending moment in on that free body cut in their positive directions. All right, so if I do that, let me use red. Here's going to be my cut at the midspan. That means I know this distance is going to be L over 2. So my free body diagram is now going to look like this, or this distance is L over 2. I have my reaction over on the side at A, which is W0 L over 2, and I have the portion of the distributed load that is on this cut that I have, that's still W0. And here's the important part. My positive bending moment puts the beam top in compression, so that's where the arrowhead goes on the top, and a positive shear force points downward when I make the cut this way. Now whenever we make a free body cut, we are completely free to choose which half of the beam we look at, or which part of it we look at. In this case, we looked at the left half, and we drew those reactions accordingly. Instead, if we want to look at the right half, on the right side of the cut, let's go ahead and draw that free body diagram too. I have over here 1/2 W0 L. I have the portion of the distributed load coming down, there's W0. I know this distance is L over 2, and I have my cut spot right here, and my internal bending moment puts the top of the beam in compression. It goes that way, and my internal shearing force points upward when I am on the left side, when I have cut, and my cut is on the left side of my section. Notice how these internal shearing force and bending moments oppose each other. This bending moment goes counterclockwise, this bending moment goes clockwise, this shear force goes down, and this shear force goes up. That's the Newton's law in action, equal and opposite reactions. If we are consistent with the way that we do this, we will get the same answer no matter if we look at the free body diagram on the left or the free body diagram on the right. But we do have to be consistent. I want to try to keep emphasizing that. So now in order to find the shear force and bending moment, let's use this left diagram. If I do the summation of forces in the y direction, I'll have plus 1/2 W0 L minus the statically equivalent force from this distribution. You notice how I'm dashing it in to indicate an equivalent force. So I have 1/2 W0 L because the length of the beam section is L over 2 and the distributed load is W0. And I have minus V equals 0. Well, in this case, the shear force at the midspan is equal to 0. Just happened to work out to be that way in this particular problem. And then if we want to do the summation of moments, and a lot of books do this, and I'll do it too, they say that the cut point right there is position O. If I do the summation of moments about point O, I'll take this way positive. I would have my internal bending moment M. I would have the statically equivalent force in the positive direction of rotation. So I have 1/2 W0 L, and then I have the moment arm length to get to the statically equivalent force, which is half of L over 2, which is L over 4. Acting in the negative sense of rotation for my bending moment, so I'll have a minus. I have the force reaction W0 L over 2 times its distance, which is L over 2 from point O, equal to 0 for equilibrium. I can solve for my bending moment. Let's see if I can do the math. I have taken this to the other side, a plus W0 L squared over 4 minus a W0 L squared over 8. Okay, so that's 2 over 8 minus 1 over 8. That should be a positive 1/8 W0 L squared for this particular example. So some of your homework problems will involve making these beam cuts and just finding the reactions at particular points. Let's take a look at another way that some of these problems are sometimes worded. Sometimes in our book they will say something like, find the shear force and bending moment at position B plus, and they'll show you a beam. Here I have a simply supported beam with a load P, and that load P is right at that point B. Now what they mean by at position B plus means just a little bit to the right of point B. So point B plus, free body diagram, would look like this, where I include the force in this picture. I have my reaction, maybe that's AY for point A. Okay, and here's my internal shearing force and bending moment. So here's my free body diagram at B plus. Now, this distance, let's make up a number, let's say that's L over 4, is such that the distance is L over 4 in this picture for the purposes of computing those bending moments. We are just a tiny bit to the right of point B. That means include the force B. If we say at position B minus, then what that means is we would make a free body cut where we go just a little bit to the left of point B. So here we have my reaction AY, and it's just a little bit to the left, so that means this distance is still L over 4, but now I don't include that force P. But I still have my V and my M. So just to make sure we kind of distinguish between those two, here maybe I'll put this, label this as B plus, and here I'll label this as B minus. And you might remember from statics doing shear force and bending moment diagrams where you had vertical jumps. Basically what this is saying is we want you to be to the right of the jump or to the left of the jump, because if you're right on the jump, it's kind of undefined. All right, let's look at another example. And in this example, we're not interested in finding the shear force and bending moment, the internal shearing force and bending moment, at a specific location, but we are interested in finding the internal shearing force and bending moment as a function of position x. So on my beam, I have some load. Here's a triangular distributed load. The length of the beam is L. My coordinate system starts at the wall and goes to the right. I need to make a free body cut at an arbitrary position x. Now, to emphasize that I'm making the cut, let me switch colors. I'm going to cut this at some position x. That means that the distance from the wall to that cut is distance x. And if you look, if the entire beam is length L, that means that the remaining distance is L minus x. Now, again, when we do a free body diagram, we have our choice of looking to the left of our cut or looking to the right of our cut. The choice is ours, but I'll tell you what, in these kind of problems with triangular distributed loads, you're probably going to be better off if you look at the side of your beam that includes the tip of the triangle. If you do everything right, it doesn't matter, but you'll have less work if you go to the right of the cut in this case. So let's draw our free body diagram looking to the right side of my cut. So here's my cut. Here's my beam. I know this is distance L minus x. And I have part of this triangular distributed load. Now, it's important to realize that the height right here is not W naught, but it's something less than that. I don't know what it is right now, but we'll find it out. I'm going to call that height H for right now. Now, on this cut goes my shear force and bending moment in their positive directions. I'll just call that M and V. And notice positive bending moment puts a top in compression, and the shear force, when I'm looking on the left side of my picture, goes up to be positive. Now I need to find that height H so I can find the statically equivalent force of that portion of the triangle. And this is where something called similar triangles comes in. Now, we've talked about this a couple times already in this class, but if you look at a small triangle that has these dimensions, those dimensions are in the same ratio as a triangle that has these dimensions. Okay, so let's write it down. H to L minus x is equal to W naught to L. So if I want to find out what the height H is, it's equal to W naught over L times the quantity L minus x. So the statically equivalent force from the triangle then is 1/2 the base times the height and it occurs at a distance of 1/3 of L minus x. So if I call this cut position O, if I do the summation of forces in the y direction, I'll have V minus 1/2 W naught over L times the quantity L minus x squared equal to 0. So my shear force equation is going to be equal to 1/2 W naught over L times the quantity L minus x squared. And if I do the summation of moments about point O, if I take that way positive, let's see, I'll have minus M, and let's see, that rotates this way, so minus the force times the moment arm distance, which is 1/3 of L minus x, equal to 0 for equilibrium. And if I solve that for my moment equation, m, bring the m to the other side, I'll have minus 1 over 6 W naught over L times the quantity L minus x cubed. Now what these equations do for us is anywhere along the length of the beam I can put in a value for x. L over 4, L over 2, L, and these equations will tell me what my internal shearing force and bending moment are. Now while we're here, there's something I want to point out about these equations. If we look at these equations kind of closely, there is a relationship among them. Here we have V is 1/2 W naught over L times quantity L minus x squared. Here we have M is equal to minus 1 over 6 W naught over L, L minus x cubed. If I were to take the derivative of the bending moment equation with respect to x, I would get the shear force equation. That's in a relationship that we will see in more detail in the next lecture. But I want to point that out now. When we get ready to talk about shear force and bending moment diagrams, we'll more formally see where that comes from. Okay, so this is an example of finding shear force and bending moment as a function of position x. Now there's one last thing I want to mention, and that is if your load is discontinuous on your beam. So I have a portion of a constant distributed load over half the beam, and on the other half I have a triangular distributed load in this example. Then we can find an internal shearing force and bending moment for each region of the beam. So there's region 1 that goes from here to here, and region 2 goes from the middle to the end, the right side of the beam. So we would make a free body cut after we find our reactions inside region 1. And find a V1 and an M1 where this is the distance x if our coordinate system starts here. And in region 2, we have that height that we need to find again. We have an internal shearing force and bending moment M2. Now we have to be a little bit careful when we do these kind of cuts. Our coordinate system has to stay where we put it down on our paper initially. Usually that means on the left side. So on this free body diagram, this distance would be L minus x. Okay, don't make another coordinate system. Stick with your original coordinate system. The point is, if your load is discontinuous, we need to make 2 free body diagram cuts to find an M1 of x and a V1 of x. And in this other region, an M2 of x and a V2 of x. Now there are some advanced ways to actually write one moment equation. That's using something called discontinuity functions. It's not taught very frequently anymore, but if I have enough time, I'll do a lecture on discontinuity functions. It's kind of slick, but it is a little bit more mathematical than this approach. All right, so we got a chance to talk about beam reactions. We got a chance to talk about internal shearing force and bending moment, sign conventions, free body diagrams, and just using statics to find internal shearing force and bending moment. Usually this is a pretty straightforward assignment, but if you do have any questions, please let me know.